right, it's working for now. Let me switch over to the laptop. Desktop. All right, so I had a little funny joke for you guys that I forgot to show on the first day of class. So things in organic chemistry, the main one is how to draw the perfect hexagon. That is really going to be true in this class. You guys will be so good at drawing hexagons. If you think you're just going to suck at drawing hexagons, there is a way to work around this. People actually do make templates that are out there that have all the different shapes. And then I did see that someone in this class already had this kind of notebook. It's called a Benz note. So B-N-Z note. And basically, it's like your standard graphing paper, because everything's a hexagon. And where is she at? You had one, right? Yep, it's pretty awesome. And you can actually just use that to draw it. Another thing I've seen people do to get around it is you can actually just download these PDFs and put them into a Word doc and print it. So if you want to just make your own, they're not as nice though as if you just bought the book though, because they end up being kind of dark if you print them out. Where the ones in the actual book themselves are kind of light, so they don't show through too much, and you can use them. So whatever you got to do to get the drawings, right? And there's actually certain times in this, I'm thinking mainly later this semester and one time in OChem 2 where we're drawing so many hexagons. I'll actually bring a page that has like a bunch of hexagons printed on it already, and that'll be lecture notes for the day. So, all right. So I wanted to jump back into the PowerPoint that we were working on last time. I believe we ended here, and we were starting to go over the bond orbitals and that kind of stuff. All right. Switch over to that. All right. So, like I said, last time we ended here, I wanted you guys to know up to 4 groups. So when we're talking about the number of electronic groups on there, we're basically looking at bonding and non-bonding groups. Do you guys remember if there's a difference between, when counting bonding groups, if there's a difference between double bonds and triple bonds and single bonds? We actually consider them in the same fashion. So they're just groupings of electrons. We're not necessarily worrying about the number of bonds there. So for example, something with a linear shape, that could be something like a triple bond on one side and a single bond on the other side. That would be a linear geometry. So we're not really worried about the actual bonds there, just if there's bonds there or not. And then on that note, you do want to count the non-bonding ones as being separate because they don't end up aligning in the same orientation in space. So they still will form a tetrahedral. They're not all going to kind of clump up on one side. So you definitely want to do some practice with these, and if you do enough practice, you're definitely going to hit all the different examples here. And recall from last time, I also said that you're not going to go to 5 and 6 groups. So none of that none of the octahedral stuff or the trigonal bipyramids, none of that stuff in this class. So 2 groups, 3 groups, or 4 groups. So it's not too much, right? And the main reason why we're only sticking to the tetrahedral and up is because we're talking about carbon mostly, right? So a lot of the other chemistry of the elements that actually do those octahedrals and whatnot, we're not even talking about in this class. So, all right, different types of geometries that your carbon can have. So notice here, the linear one on the far right, that's what I was talking about with the 2 groups. Does not matter if it's 2 doubles or a single and a triple. We're just calling them groupings of electrons. In drawing their shapes here, notice that one says trigonal planar. So when things are planar, that means that they're flat. So you don't want to actually draw them 3-dimensionally. Just draw them flat on your paper. And by drawing them flat on your paper, you have drawn in 3 dimensions. All right, bonding and anti-bonding stuff. Talked about that a little bit last time. Different geometries. Going to kind of skip ahead here a little bit. I wanted to show you guys something for figuring out what kind of geometry they have. And I think I'm going to switch back over to the dot cam for a second here. All right. So I mentioned to you guys last time that if we have the single bond between two atoms is defined as a sigma bond, and then anything additionally past that's a pi bond, right? There's a way to quickly figure out what the hybridization is, and something you want to think about when you're doing this is, if you recall, a single shell here has these two different subshells, the s and the p. There was only one s orbital and 3 of the p orbitals, right? So what you can do is you can count how many electron groups there are. So how many you guys see here? There are 3 groups. So you can literally just count left to right here. So it goes 1, 2, 3. So what will happen is that these 3 will combine into 3 different hybrid orbitals. So we're going to call this an sp2 orbital because there are 2 p orbitals that are in combination there. So 1, 2, 3. These hybrid orbitals are going to be your sigma bonds. Your first bond that goes between 2 atoms, that is your sigma bond. Like this. And then what is left over, that is your pi bond. And any additional bonds. Like that. So just by seeing that we have 3 electron groups, that tells me that we're going to have 3 sigma bonds and 1 pi bond. And are you guys seeing that also in the original drawing as well? So the first bond between something would be a sigma, and then the additional double bond here, that is your pi bond. We could do a similar thing too with the sp. So an example of that would be something like this. Carbon with a triple bond on one side and a single bond on the other. That's a linear geometry. If you were to just see that, what I want you guys to kind of visualize is that, so instead here we're going to count over 1, 2. So it's going to be an sp orbital. There are 2 of them. And then how many p orbitals are left over? There are 2 left over p orbitals. So then how many pi bonds am I going to have? 2. Yep. That's essentially what's happening here. Is these hybrid orbitals first form to make your sigma bond, and then the leftover p orbitals become your pi bonds. And that's why they end up being above and below the plane of the molecule. All right, so let's go ahead and switch back to the PowerPoint. Showing up okay, showing up okay. All right, so we just talked about the sp2. So here's what's happening. So first we have our hybrid orbitals that go right between the 2 atoms. And then the additional bond is above and below the plane. So I want to point out here that this whole thing, is my mouse showing up on the screen? No, it's not. That part on the right, that orange and blue part, that whole thing is the pi bond. So don't think of that as 2 pi bonds. That whole thing is a pi bond. So the left is illustrating sigma bonds. The right side is demonstrating a pi bond. And then putting it all together, this is kind of what it looks like when it's all together. And don't worry, I'm not going to have you guys draw this on paper, but I do want you to understand what's going on. And if I were to give you a drawing, if you could label the drawing, like what's sigma, what's pi. Just don't worry about drawing the stuff. You could draw for practice. I do believe on the worksheet, the activity 1.1, I ask you to draw it. That's just to get you guys to practice it and to start figuring things out. So I just want to be clear here. I am not going to have you guys draw it. I did that one semester and it was horrible. Some people can't draw very well. All right. Similarly here with the triple bond, you get 1 additional pi bond. And do you guys remember what happens to the bond length as you start adding more bonds in there? They start to shrink, right? And you kind of think of that as if you had 2 big balls and you're kind of putting a new spring between each time, they're going to start holding closer together. The one thing I want to point out on this particular drawing here is that the 2 pi bonds are perpendicular to each other, meaning that they're 90-degree angles off from each other. That will come into play. The reason why I'm putting so much emphasis on the kind of geometry that these pi orbitals are making is because that they do affect reactivity. So the reactivity of a sigma bond and a pi bond are completely different, and it has to do with their arrangement in space. We're going to see that later on this semester that pi bonds are more reactive because they're away from the atoms a little bit, so they can go out and grab something. So that'll come into play later on, probably about half through the semester. All right, so here's what I was just talking about. As we add the additional bonds, the bond length shrinks. And what happens to the bond strength? It increases, right? So as you have more of those springs between it, the stronger that bond's going to be. All right, non-bonding groups, basically, once again here, they influence the shape, but they are not part of the shape, and you definitely want to learn the chart that was earlier. Here's another version of the same kind of thing here. So we have an illustration of a tetrahedral. And notice how if we have a non-bonding group on there, it becomes a pyramid, and then two non-bonding groups, we say it's bent, but electronically, it's still a tetrahedral. All right, this is kind of summarizing the same kind of thing here. All right, so here's polarity. Polarity comes when you have atoms that are not of the same type bonding together. So essentially what happens, each individual element has its own electronegativity, and if there's a large difference between the two, you end up with a polar bond. And I'm hoping this is a review. This should not be new for you guys. Basically what we look at is if there is an overall directionality of the dipoles in the molecule. Do you guys remember why we don't have any arrows drawn on the CH bonds here? Well, CH bonds, the dipole moment between them is so tiny that we essentially consider them to be nonpolar. So they're negligible basically. So if you're looking at, and that's really useful for carbon compounds because they have a lot of CH compounds in there, or CH bonds in there. So typically things that have something that's not carbon or hydrogen end up being polar. So here we have a chlorine atom on there, that makes the compound polar. And that makes the carbon atom electron rich or electron poor. Which one is it? Electron poor. Yep, it's pulling electron density away from carbon, making it electron poor, which then means that it can start reacting by pulling electrons towards it, but we're getting ahead of ourselves here. The main thing I want you guys to be able to do here is identify if something is polar or nonpolar. Something else I want to mention here too is looking at polarity. You guys probably learned in your general chemistry class that things are polar or nonpolar, like dissolves like, that kind of thing. And it turns out that whether things mix together or not, it's kind of a gray scale. It's not black and white. So yes, this compound technically is polar. That will not go into water. That's chloroform, I believe that one is. No, sorry, that is pretty close to dichloromethane. A lot of these methane solvents do not mix with water. Even if they are polar, they're not polar enough. All right, so once again here, what we do is we look at the overall, we look at the arrow drawn for each dipole moment, and then you look to see if there's an overall directionality to the arrow. So the first compound being ammonia, everything is pointing toward nitrogen, so that makes the compound polar. And similarly with the water molecule on the right, everything is pointing towards oxygen, so it's going to have a net direction to it, so it is polar. Okay, as you go through your textbook, you may see these electrostatic maps there. They're basically a kind of a colored representation of what we're talking about here. So typically the red ends are the delta minus end, and the bluish colors are delta positive. There are times later on in the chapter where they will discuss reactivity of molecules, and we'll be using these kind of maps to do it. At least your textbook should be. I don't do it too much on the overhead here. All right, moving along here, we did have some intermolecular forces that you should have talked about in Chemistry 121. The main ones here are dipole-dipole interactions. That's basically when you have two dipoles kind of attracting to each other by opposite charges. We have the hydrogen bond, which is actually a special case of the dipole-dipole. It works in the exact same fashion. Do you guys remember which atoms are involved in hydrogen bonds? Like which? So you have hydrogen paired with what other? There were three atoms that you can pair it with. There was oxygen, fluorine is one, and then what is the nitrogen? Yep, so it's oxygen, nitrogen, fluorine. So if you have a molecule that has an OH, an NH, or an FH in it, it is possible for it to have a hydrogen bond. The reason why we have hydrogen bonding as its own special category here is because it's very prevalent in nature, because water's everywhere, and it's also very significant for biological systems. Because you guys probably learned a little bit about hydrogen bonding being in biological systems. The main one I'm thinking of is that's kind of what holds DNA strands together. The two DNA strands are held together by hydrogen bonds, and proteins basically unzip it to open it. The last one here is dispersion forces. That is the case where the molecules are typically completely nonpolar, and they are being held together by subtle changes in the bulk structure over time. So at any given time, the electrons could be on one side or the other. Because remember, electrons are always moving. So you have a situation where one side could briefly be positive for like a microsecond. And then that kind of propagates the whole structure and kind of holds things together that way. So once again, dispersion forces typically only happen with things that are nonpolar, and they're typically only significant if you have a really large molecule. Really small molecules do not exhibit significant amounts of dispersion forces. All right, so here's this more illustrated version of what we just talked about. So the dipole-dipole, that's where you have the slightly positive, slightly negative on one side, and they're kind of holding together by opposite charges here. And as we just talked about, the hydrogen bond is a special case of this. This one is kind of the same as a dipole-dipole, but in this case, instead of having a partial charge, we have a full charge. So this can happen with an anion or a cation and any polar molecule here. So here it's showing that this is happening with water. And this drawing here is actually referred to as a solvation. That's when solvent molecules can surround a solute, and that is actually required for a compound to go into solution. So if the compound does not have any kind of ion dipole or dipole-dipole interactions with the solvent, then it's not going to go into solution. Similarly, if some particular solute only exhibits the dispersion forces, that means the solvent should only be exhibiting dispersion forces also. Basically meaning like dissolves like, right? In order for that like reaction to occur, it must undergo or must exhibit solvation. Otherwise, it's going to fall to the bottom of the solution. Here's just an example here that sometimes you can get salts to dissolve into organic solvents. You would think that they wouldn't, but they actually do via ion-dipole interaction. So this compound is actually acetone. Acetone is miscible with water, and it turns out that some salts are as well. And here we're showing a lithium ion being solvated by acetone. Dispersion forces. This was the case with the nonpolar compounds when you have the large structures exhibiting within a moment in time an unequal sharing, and that kind of propagates to the whole mass of the structure or all the different molecules involved, making them stick together. And just to be clear here, this only is typically important with large molecules. So things like lard, which has like 30 carbons in it per molecule, things like that stick together really well. But things that are small molecular weights like methane do not stick together well because they have poor dispersion forces. They will just separate out. Do you guys remember the impact of intermolecular forces on things like boiling point? So suppose something only exhibited dispersion forces. Would you expect it, and it only had dispersion forces and had a low molecular weight? Would it have a high or low boiling point? Low boiling point, because basically the stronger the dispersion forces, or sorry, the stronger the intermolecular forces are, the stronger the molecules can kind of stick together, and they're not going to want to boil away. So the weaker the forces are between each other, the weaker they hold together, the easier they kind of just go across in space. So if something is able to exhibit things like dipole-dipole or hydrogen bonding, that are pretty strong intramolecular forces, that tends to have a dramatic effect on the boiling point. So things like water boils at a pretty high temperature compared to other things of equivalent molecular weight. All right, here just an illustration of the hydrogen bond in a structure of water here, just a bunch of water molecules sticking together. This is actually, you guys probably learned this before, but this lattice structure is why frozen water will sit on top and not sink. So for most compounds out there, if you freeze them and put them into their liquid form, they typically fall to the bottom. So if you were to freeze something like benzene and then throw it into liquid benzene, it'll fall to the bottom. Water is exceptional because of the fact that the hydrogen bonding makes little pockets form in it, which are effectively acting like air bubbles. So you can think of it as like a piece of styrofoam, essentially, at that point. Here's just illustrating that you can have the same thing happening with carbon compounds. These are methanol. They are a type of alcohol. They have hydrogen bonds also because they have OHs in them, just like water does. What do you guys think will happen to the significance of the hydrogen bonding as the carbon structure starts to grow, meaning you have more carbon pieces? Do you think that'll have an impact on the amount of hydrogen bonding that's possible? Yes. And there actually is a direct correlation between whether or not an alcohol is miscible with water by the number of carbons it has in it. And it all has to do with the carbon pieces starting to disrupt it. It's starting to become more organic-like or more dispersion forces, which is not miscible with water. I'm getting ahead of myself here. We'll talk about that later on in a little bit more detail, probably next semester. All right, solubility, that we just talked about here, the like dissolves like. Polar compounds generally mix with other polar compounds. So in general, like water and salts mix together. A lot of these non-polar solvents we're going to work with this semester do not mix with water. So you guys probably all seen this before. Oil and water do not mix, and this is due to their difference in polarity. So what do you guys think? If I were to say take a pinch of table salt and put it into a cup that just had vegetable oil in it, do you think the salt would go into the vegetable oil? It doesn't. You can try that at home if you want. Salts will not dissolve in vegetable oil, but they will in the water. And that all has to do with the difference in the polarity here. Notice here too, I do mention that the less dense liquid should be on the top. That is going to be a situation we have in lab. We're going to have a funnel that we're going to be using to separate two different liquids that look just like this, where we have the two layers. And you're going to have to know whether or not which layer is aqueous, which layer is organic. And there are tricks to figure that out, but in general, if you look at the density of the two solvents involved, you can figure it out that way. The less dense solvent will be on the top. And we'll see that in, I think it's like lab 3 or 4, we start doing that kind of stuff. Another thing we're going to see in this class too is we are going to use some acid-base reactions to kind of play around with polarity a little bit. So we're going to have these compounds that are really large carbon structures that have an acid group on it. And if the compound is neutral, meaning it has no charge on it, it'll act like your typical nonpolar compound. But if you were to remove one of the hydrogens on it, give it a charge, it then readily goes into water. And then we can bring it back out of water by giving it that hydrogen back. And we're going to play a little bit with solubility by changing the charge on molecules. And that's kind of what's being shown here. This actually looks like what we're going to be doing later on. This particular compound was an acid compound, had an extra H. And then you making it soluble in water, and then you add your base to it, getting rid of that extra H, makes it fall out of solution because it no longer has the right polarity to be in the water. But yeah, we're gonna play around with solubility that way. It is kind of cool because it's almost instantly this precipitate form that you can't even see. All right, here I just want to briefly talk about how soap works. It is related to polarity. Does anybody know where we get those molecules from? Anybody with any kind of little bit of biology background? The top ones there. Those long carbon chains with the polar head. or fatty acids. You guys know exactly like, well, basically a fat compound has a glycerol head and a fatty acid tail. And we do a reaction called saponification, basically breaks off all the fatty acid tails, and those are your detergent molecules. What happens here, as we see in the drawing, is that the nonpolar region, all the carbons and H's can plug into, like the hamburger grease on your t-shirt, and then the polar part will kind of stay towards the water. And then what happens is that as you wash this away, the water goes away, it grabs the polar heads, pulls everything along for the ride. The big thing about cleaning in general is getting things to go in solution. And this allows organics to go into solution. And the hardest thing to get rid of while you're cleaning are the organics. So things like oil and grease, those are the hard things to get rid of. And the main reason why is because they're not soluble in water. So to illustrate this, you can try washing a dirty, greasy pan with just water and no soap, and how long will that take you? And then you just put 1 drop of soap, it all just goes in solution. And it's because it's forming these kind of structures. There is a problem, however, with using these kind of compounds, is that they are readily precipitated out of solution with calcium and magnesium. And is that significant in Las Vegas, having calcium and magnesium in our water? Like, do we have calcium and magnesium in our water here? Is it a little or a lot? A lot, yes. We have hard water here. Hard water here is, calcium, magnesium. And it turns out that if we were to use these kind of detergents, it would make so much crud that it would clog all of our pipes. So to get around that, what people did was they changed the head there to a phosphate group. Does anybody know the problem that happened with phosphate detergents? Like, what is that? Is there any problem with that? What's that? One of the problems is when it actually gets out to natural bodies of water, and especially the ocean in particular. It turns out that these phosphate detergents are one of the favored foods of algae, and they result in algae blooming. And what algae blooming does, it basically a ton of algae grows all at once. They actually are kind of pretty looking because they have like bright reds and green colors. But the thing is, they take out all the oxygen from the water. And oxygen, fish need oxygen to live. So after they suck all the oxygen out, all the fish start to float at the top because they're all dead. And it's actually really bad for aquatic wildlife because the algae just takes over at that point. So to get around that, we now use Syndets, or these sulfur detergents now. So they serve the exact same purpose. They do not precipitate out of solution with calcium and magnesium because sulfates typically don't precipitate that easily. And we don't have to worry about them feeding the algae. So these are the current stuff that we're using nowadays. All right, and that is it for the first set of material. Yay! Did you guys have any questions about anything? Go ahead.
On the second PowerPoint, I don't know if it shows it for you, but for me, towards the end of the PowerPoint, it starts to get messed up. The words start to...
On the second PowerPoint you said?
Yeah, 1.2.
All right, I actually have it downloaded right here, so we'll see. I downloaded it from Canvas instead of my own computer. Did you click the enable editing thing when you opened it? Okay, because sometimes you'll get an option for enable editing, and if you don't click it, sometimes the formatting is weird if you don't say okay. All right, guys, I wanted to get through parts of this here. I'm hoping actually next week we're starting into infrared spectroscopy. No, we actually have a little bit of time. I'm hoping that next week we'll have a little bit more time for some practice problems. So what my hope is that you guys can go, this weekend review the stuff that we've covered so far, and come to class on Tuesday next week with questions. And you have a little bit of an idea like what you're trying to figure out. If you're having trouble with anything, you are more than welcome to stop by and talk to a tutor. On that note, I do believe that we have we currently have 2 organic chem tutors, and we're going to have a 3rd one here pretty soon. He just applied yesterday, so I'm pretty sure he's going to get approved. He got an A in my class. I'm pretty sure he's going to pass the little test they give him. Because if you get an A in OChem, you can pass our tutoring test. It's not that hard. But you have to have taken OChem, right? So, all right, let's go ahead and... All right, so structure drawing. So we did talk about earlier how we're going to be stepping away from this nasty method. There are things from NASU or doing those simpler Lewis structures that you should be taking away to here. Things like the octet rule, non-bonding electrons, geometries, that kind of thing. Still go into organic chemistry, but the way we approach organic molecules is completely different. So the things that we're going to be stepping away from is things like counting valence electrons. I never do that when doing organic structures. I only do that when I'm doing these simpler inorganic ones. You shouldn't have to anymore. So we're going to go over a little bit over alkanes. My goal for today is to start doing some bond line drawing. So basically, it's the alien language of OChem, right? when I have all these drawings out, my wife says I'm writing an alien. She's like, when are you going to start your crop circles? Maybe next year. All right, so first things first, did you guys do or cover a little bit of organic chem at the end of 122? I know most of the teachers get to that point. I'm guessing you guys probably did a little bit of naming, right? Is that about what you did, naming? Did they go over functional groups with you guys? Okay. Because they were asking me what I think that they should cover, and I said do alkanes and alkanes, nomenclature, and functional groups. And I think that's probably what they did with you guys. So hopefully that's the case. Anyway, alkanes are your simplest organic compounds. They contain only carbons and hydrogens. And a particular note is that everything is single bonds. There are no double bonds in there. Because they don't have any kind of different types of atoms in there or double bonds, they tend to be pretty unreactive. So the main thing that they're used for are mostly used for fuels and solvents. And we start getting to the larger molecular weight ones, they start becoming good for lubricants. So here we have a breakdown of essentially what happens in the cracking process of crude oil. Essentially what they do is they heat up all the crude oil, and they have a setup where it pulls off different fractions at different boiling point ranges. And each boiling point range has its own little uses to it. I'm not making you guys memorize this. I'm just explaining where alkanes come from. So do not memorize this chart here, please. That's table information. So the main takeaway here is that the higher molecular weight ones are not as volatile, and that have a direct correlation with what we were talking about last PowerPoint with the intermolecular forces. So as you have more carbons, heavier molecules, they tend to stick together easier. They're not going to boil away easy. So that's why these things at the very bottom there have high carbon counts. They're things like lubricating oil and asphalt. I do know that typically that after they boil away the crude oil, that sludge at the bottom becomes road tar, usually. So typically when they're smearing that tar on the road, it has that blackish color, it's because it's from crude oil. All right, there are numerous ways to represent different compounds. The way you guys have been drawing them in the past is this way. We don't really use that anymore. The reason why is because that doesn't tell me a lot of the detail that we need to know in organic compounds. Like I need to know if that compound has an OH in it or it has a COC in it. That makes a difference. That affects the polarity, affects the reactivity, affects everything about the properties of the molecule. That's why functional groups are so important, because they basically impart their reactivity. But the thing is here though is that one way to draw things is, so the one on the left is the Lewis structure there. You could also draw it in 3 dimensions. And then we use the condensed formula pretty commonly too. So instead of writing out all the H's out, they're just kind of scrunched together to show you how many there are. Oops. Here's another way to show them. So here we have some tetrahedrals. I found this drawing on the internet. I have beef with it now that I see it up on the screen. I hate the way they do the tetrahedrals on the second and third carbons on the first structure. So that was the way I was describing to not draw them. You want to have the lines that are in the plane on one side of the molecule and the dashes and wedges on the other side. They're kind of intermixing it in this drawing. The reason why this matters is because when we start getting to handedness of molecules, this will lead to wrong answers drawing it that way. But my point is here is that there is a couple ways to draw these molecules. You could draw them as either a string, writing CH3, CH2, CH2, CH3, or you could actually draw it out and draw everything out explicitly. Depend on what you're doing, which method you're going to use. As we progress, though, we're going to get away from even writing letters at all, right? If you guys seen those organic drawings before, we don't really draw any letters at all anymore. All right, there are numerous ways to stick these molecules together. Unfortunately, there is no actual equation that we really use to determine the number of possible isomers there are. And this is one thing that I want to actually practice next week, is that if you're given a formula, draw out all the different isomers. And basically what that means is how many different ways can we put the molecule together. I probably would not put a C8 on the test. That would be kind of ridiculous, because that's 18 different possible ones. I would use something a little bit smaller on a test with you guys. All right, so the reason why we're building up to doing a shorthand or the bond line drawing is, here's a good example here. We have amoxicillin. Do you guys know what amoxicillin is? What is it? It's a very commonly used antibiotic. It's the blue pill, isn't it? Remember right? It's the blue one? Which is the antibiotic that's blue? I don't know. It's going to be different to the manufacturer. The point is here, though, that the structure on the left is amoxicillin and the one on the right is. What is the difference between the two? Which letters are not written? Hydrogen are not written, neither are carbons, are they? So basically what we're going to be doing here is all the carbons and H's are going to be implied, and all the non-carbon H's must be shown. Additionally, any H's that are attached to a non-carbon must be shown also. And those are referred to as heteroatoms, but we'll get there in a minute. But part of the goal today is to learn how to do some bond line drawing. And if you see a bond line drawing, you basically want to see like the left drawing in your head. So you have to be able to go back and forth between the two. Okay, typically when you draw straight chains, you want to draw them in a zigzag. And what's happening here is for your bond line drawing, each carbon is assumed to have a satisfied octet unless it's shown to not have a satisfied octet. So meaning that it has 4 bonds, right? So basically what we have here is that each end of a chain or kink in the chain is considered to be a carbon atom, and any bonds not shown are assumed to be H up to 4 bonds. Does that make sense? So once again, each end of a chain or bend in a chain is a carbon atom. They are assumed to have 4 bonds, and anything missing not shown is assumed to be H. What this drawing is showing here is that these molecules can kind of bend and twist. These are all the same molecule that are shown there. We're going to actually go over a whole chapter talking about the spinning of bonds and how they can spin in space here. We do draw them in zigzags, though, and the reason why we draw them in zigzags is because there is a happy conformation they want to be in, and it turns out that alkanes like to be in a zigzag shape. And we'll go over that in full detail like a couple weeks from now. Here is another way to show this, and here we have our first hexagon of the year. So essentially each of the carbons is shown to have 2 bonds on the right drawing. So then what is implied are the 2 H's are implied. And then you can compare that to the structure here. One thing I want to show you guys, though, that if there is shown to be a non-zero formal charge, so for example, we have something like this. How many bonds do you think carbon has now to it on the one with the plus charge?
3.
Only has 3 bonds to it now because it has the plus charge. So that particular carbon with the plus charge only has 1 implied H. So basically, we assume H's till we have the right formal charge. So if it's 0, that means that carbon has 4 bonds to it. If it has a formal charge of +1, that means that carbon only has 3 bonds to it. It's missing one of the bonds. Getting a little bit ahead of myself here, but to go.
Why is your equal sign like 3?
It means they're equivalent.
Oh.
Yeah. Basically, people use that sign when they're saying equivalency rather than using like a mathematical equivalent. All right, this one right here too. I am particular about certain ways to draw these, and the main thing here is for heteroatoms. Heteroatoms are anything that are not carbon or hydrogen, and you guys see the difference here between the way this is shown? Notice how this one, the NH2 is pointing that way, and this one's pointing this way. And the reason why you don't want the NH2 to point the same way here is because you're not clearly showing the carbon-nitrogen bond. Showing it this way or this way clearly shows the carbon heteroatom bond. And that's what I want you guys to get in the habit of. So don't show them going to H unless they actually are going to H. All right. As we just said here, atoms are bonded at angles, zigzags that represent the absolute geometry. So that actually is a 109.5 degree bond angle. That's the bond angle for a sp3 hybridized carbon. And once again here, each of the N's or bens is a carbon atom, and we assume the number of H's such that we have the desired formal charge, which in most cases is going to be 0. All right, so I want you guys to help me here. In the leftmost compound, how many carbon atoms are there?
4.
There are 5. Do we have a yardstick here somewhere? My mouse is not showing up on the screen, is it?
Is it?
Is it? Oh. Now it's there. There we go. Yep, so counting, it's 1, 2, 3, 4, 5. Next question I have for you guys is this carbon right here has how many hydrogens? 1. And then total hydrogens, how many do you guys think? 3. I'm counting 12. Is that what you guys got? Yeah, so just to summarize again here, this one on the end, it's only showing 1 bond to carbon. So we're implied to have 3 bonds to H. And that's the truth for any of the N ones. And then the ones in the middle here, this one only has 1. This one is shown to have 2. 2 are implied. All right, let's take a look at the one on the far right. How many carbons are there?
6.
So I am seeing 1, 2, 3, 4, 5, 6. How many H's are on this carbon?
0.
There are 0. It's already shown to have 4 bonds, and carbon cannot have more than 4 bonds. I did talk earlier today about violation of the octet rule. Carbon cannot violate the octet rule. So anytime you draw a carbon atom that has more than 4 bonds to it, it is automatically wrong. And a little funny note here, my teacher, when I had organic chemistry, called them Texas carbons, because everything's bigger in Texas, they're saying. He actually took it so far that his TA had a little Texas stamp that he would stamp on your paper anytime a carbon had more than 5 bonds to it. Like, wow, it took it a little too far. You guys want to see if you can figure out what the molecular formulas are? Let's go ahead and do the molecular formula for the middle one. So first things first, how many carbons are there? There's 6, and then how many H's are there? So there's 3, these all have 3. So 3 times 4 is 12, and then we have 13, 14 here in the middle. Yep. We're actually going to be building up to something in this chapter here where when I personally do these now, I just count the number of carbons, and then you can actually back calculate to the number of H's. There is an equation that we're going to see here today. It's the 2n plus 2, yeah. Yeah, so if you have no double bonds in there and no rings, you can say that there's a 2n plus 2 number of H's. But that rule goes out the window, though, if you have any double bonds or rings in the structure. All right, and then we do show double bonds and triple bonds, as you may expect. The thing is, though, that you want to show the correct bond angles. These are linear, so we show a straight line. But I have a question for you guys. The structure in the top left, right over here, how many carbons are there?
5.
Yep, there are 5. So be careful of this, that there are carbons here, and we're not showing them at the bend because it's linear. So we count it as 1, 2, 3, 4, 5. Additionally, on the triple bond here, right here at this carbon, how many H's are there? There are 0. Yep. Okay. If you have any H's attached to heteroatoms, non-carbons, they must be shown. They are not implied. We only imply H's if they are on carbon. Okay, and this is just another illustration about why the bond line drawing is useful. And essentially what it allows you to do is clear away all that trash and let you see the molecule for what it is. And you're going to see that we have large molecules to work with and only a portion of it that we're actually working on. So you don't want to get lost in the trees here, right? Okay, so we have a pretty important equation. I do want to mention that most textbooks don't cover this equation until way later. I don't know why. I want you guys to know this day 2. And it's the index of hydrogen deficiency. Basically what it allows us to do, we're going to be comparing formulas for how many hydrogens they actually have to the corresponding alkane. And what that allows us to do is, if we're given a formula, we'll make a comparison to the corresponding alkane, and we can make predictions on how many double bonds, triple bonds, or rings that it may have. And that will allow us to rapidly draw different possible isomers. And this is the reason why I want you guys to understand IHD first, and then we'll start doing isomer drawing practice, because this is going to help you out. So once again here, we determine the IHD. You're going to compare the number of hydrogens in an unknown compound with the number of reference hydrocarbons, which is basically the 2n plus 2. And that's going to correspond to a hydrocarbon alkane that basically has no rings, no pi bonds, meaning it's 2n plus 2. Here is the overall formula. We're going to go ahead and talk about where each little piece came from. For those of you guys that had me for general chemistry, and those who didn't, I basically, when I teach general chemistry or any chemistry class, I want people to understand equations. So one thing that I'm actually moving towards through in my 121 class, thankfully for those guys that had that a couple years ago, I'm actually going to put equations on there and ask them what they mean. So, where most people just have them crunch numbers on an equation. I want you guys to understand what it means. This is literally the only equation in this class. So remember last time I was saying that we get no calculators. If you can't do this calculation without a calculator, I question how you got this far in college. I really do. I should hope you do not need a calculator for this. All right, something that I do want to point out here, it does have a mention of sulfur. Sulfur is kind of a weird situation here. Typically, you don't want to use this calculation with the sulfur atom because sulfur can bond in a couple different ways. And you guys notice an element missing from here? That's pretty common, is what, oxygen, right? So I do want to point out that we are going to ignore oxygen and sulfur atoms when calculating IHD. All right, so let's go ahead and see what happens here. So here we have a pretty small alkane, 2 carbons. And if it's an alkane, it should have 2n plus 2, which is 6. And if you were to plug this into the IHD equation, you end up with a 0. And so what the IHD means is hydrogen deficiency. So if it has an IHD of 0, that means it's fully saturated. Fully saturated means that it's pretty much an alkane. It has all the H's it can possibly hold. If it has a number that's not equal to 0, we say that it's unsaturated, meaning that it's missing some H's. Also notice here that the way hydrogens and halogens bond, they only form single bonds to carbon. So we treat them as if they were hydrogens. So when you have any halogens in your formula, go ahead and add that to the hydrogen portion. That's why I said H plus X in the formula. You're just going to add for the halogens. And because of the fact that we get the same answer here, they're both considered to be fully saturated. No double bonds, no triple bonds, no rings. What's happening on this slide is basically on each of the structures going down from ethane, I am taking away 2 hydrogens. And in order to take away the 2 hydrogens, you have to add an additional bond between the 2 carbons, right, to make sure that carbon still has 4 bonds to it. But notice what happens to the IHD count every time you do that. So every time you lose a pair of hydrogens compared to the corresponding alkane, you increase the IHD by a factor of 1. So basically, each IHD corresponds to a pair of hydrogens. And if you're missing a pair of hydrogens, that means that you can have potentially a double bond. If you're missing 4, that means that you can have a triple bond. So notice how this one is missing 4 hydrogens in comparison, and that's because we have the 2 extra bonds in between. We lost 2 pairs. All right. So this one here is showing what happens with rings. People do technically think of cycloalkanes as being fully saturated, but their IHD is not 0. So the IHD for cyclohexane is equal to 1 because basically in order to bring the ring together, we have to lose an H on each end of the carbon, right? Each carbon end. So that ends up giving us an IHD of 1. So far we have a couple possibilities. Let's back up a second. So if you have an IHD of 1, it could potentially be a ring or a double bond. If we have an IHD of 2, it could be a triple bond, right? If you get an IHD of 2, that does not automatically mean you have a triple bond, though, because it could be 2 rings, it could be a double bond and a ring, or it could be 2 double bonds. Any combination of that. Okay, this one here is illustrating why we are going to have to add for nitrogens, and that's because nitrogen does not hold as many hydrogens as a carbon could. Nitrogen is typically happy with only 3 bonds to it, where carbon wants 4 bonds, right? So in comparison here, we have 1 less hydrogen. We account for that by adding instead of subtracting for nitrogens here in the formula. And that way you end up working out getting a 0 as well, meaning that your structure has no rings or double bonds. All right, are there any questions about this so far? One thing I do want to point out is that if you did not get a whole number for an IHD calculation, you messed up somewhere. You should always get a whole number. It should also always be positive. It'll be 0 or positive. Okay. So I think this way illustrates what I think is the hard way and the easy way to do IHD. If you are just given the structure, you can literally just look at it and count it. You don't have to actually calculate it. So the first one, how it has 1 ring, that's what IHD of 1. However, in the formula, notice how the oxygen atom is not accounted for. And it works out in the math, if you just ignore oxygen, the IHD will work out to be correct. The second one is 1 because of the double bond, and the IHD also works out to be 1 if you ignore the oxygen. And then the same thing for the last one. We have no rings, no double bonds. The IHD should be 0, and it does work out that way if you ignore oxygen. All right, here is a special case. Here we have a benzene ring. We're going to go over, we actually have, I think it's 2 chapters dedicated to nothing but benzene compounds in OChem 2. For now, what I want you guys to know about benzene rings is that they are extremely stable, and because of how stable they are very common in chemistry. A lot of biological compounds have these benzene rings as part of their structures because they are so stable. So notice here in a benzene ring, if we have a ring, and then you have 3 double bonds, that's an IHD total of 4. If we have the 3 double bonds, we have the 1 ring. My point here is that typically having an IHD of 4 or more is pretty rare unless your compound is aromatic, meaning it has a benzene in it. So if you see a compound that has an IHD of 4 or greater, that almost always indicates you have a benzene ring. And I want to say almost always, because yes, I could probably think of an exception to this rule. There's always exceptions, right? So, but in general, if you see IHD of 4 or greater, assume benzene and then work from there. All right, before we, I'm actually thinking, I'm going to stop the PowerPoint here. I'm not stopping for the lecture for the day. I do want to do a few little practice problems, see what we can come up with, and the kind of thing that we're going to be doing with this. So let me go ahead and switch over to DocCam. Document camera, and then I will display this way. So let's say a C5 H10. Okay, so a common question that you would be given is to draw all of the possible isomers of this compound. And actually, so let me just make this a little bit different. Let's do an easier one first. I want to do a C5H12 first. So when you approach a question like this to draw all the different possible isomers, I think the first thing you should do is calculate an IHD. And the reason why is because that'll kind of limit what you can do. So what do you guys think the IHD of this is? So, yep, so IHD, if you want to write everything out, is 2 times 5. Was it 2C plus 2? So we have, sorry, 2 times 5 plus 2 minus hydrogens, and then divided by 2. I don't think it explicitly mentioned it in the PowerPoint here, but the division by 2 is for the pair of hydrogens. That's why we're dividing by 2. This is equal to 0. So what did that tell me about all the different structures I draw? We're going to have no double bonds and no rings. So the cool thing is that now if you draw a structure that has 5 carbons in it with no double bonds or rings, you will have exactly 12 hydrogens in it every time. So that way it'll shorten the amount of time you're spending working on this. So I think the best one to start with is draw it out in a straight chain. So 1, 2, 3, 4, 5, and I'm going to be using the shorthand from here on out. So hopefully you guys can be okay with this. Another thing we can do is we can move a piece over. So what I mean by that is here I have the 4 carbons, and I'm going to go ahead and attack this one right here, like that. So these are now 2 different, 2 unique compounds. So what if I moved it over again? So instead of putting it there, I now put it here. Yeah, these are the same compound now. And if you're having trouble visualizing how they're the same compound, is here I have my blue pen, and by doing this, the pen did not change, right? So that's essentially what's happening here. We're going to see in chapter 4, I believe it is, when we start naming things. One way, if you know you're naming now, is that if you get repeat names, it means you have the same compound. That's a good indicator. I think there's one more way we can put this together and get a unique structure. Is that right? Did that work? Does it have 5 carbons in it? Did they have a ring of double bonds? Nope. It should have 12 hydrogens. So you guys see how this is useful? So, and if you were to actually go back and now count the hydrogens in each, which I recommend doing for practice, you'll see that you should have exactly 12 in all of them. And we did that without actually having to do that, every little time. That'll take a ton of time if you had to do that all by hand every single time. I want to go ahead and do one more. That was the C5H10 now. That was the one I was originally going to do at start. So what is our IHD in that? So IHD was 2 times carbon plus 2. So 2 times 5 plus 2 minus the number of hydrogens, which is 10. I believe the top works out to be 2. And then divided by 2, we get 1. So that tells me that no matter what structure I draw, I need at least a ring or a double bond and 5 carbons. If I satisfy that criteria, the structure will have exactly 10 H's in it. So I think the best way to start, there's a couple different ways to start, but I'm going to start with the straight chain, but I have to put a double bond somewhere. That's 1 isomer. And then I could put it 1 carbon away. And then if I move it 1 more, I'm basically making a repeat then. So at this point, I could start altering it by moving carbons around. This one's actually going to have a bunch of different possibilities. So I'm going to take that carbon off the end there and just say move it here. I could then move it here, and so on and so on. Unfortunately, there is no, I was saying earlier today that there is no set equation that we use to determine the number of possible isomers. And if I put a question like this on a quiz or an exam, I will tell you how many I want. So I will typically specify how many I want. All right. So do you guys have any questions about anything? We are roughly out of time. So I think this is a good place to stop. So we will pick up with this next time. I would like if you guys, we have a lot of material to go over, so I want you guys to practice this weekend, get caught up on the reading, any little thing that you think you need to work on, and then please come on Tuesday with questions. And don't forget, I do have office hours that I have listed. I want to talk briefly about Discord. I just want to mention here that I do not want Discord to be a replacement for Canvas. So I did get a question on there asking something about the course, and questions like that you should ask me directly through Canvas. The thing is, you don't want to rely on me checking Canvas every day, because I'm probably not going to. My eventual idea is that I'm going to try to take a back seat to it. This is your thing. So I'm hoping that you guys will take ownership of it and kind of talk with each other. I've actually entertained the idea of after you guys have been using it, of me just passing lead to somebody else and getting out of the channel. I'll let you guys just have it. So I don't really, whatever you guys want to do, but please do not use it as a way to communicate with me directly if you're asking questions about the course. That's meant for you guys to talk to each other. All right? All right, see you guys on Tuesday. Don't forget about your pre-lab that is due on Tuesday. All right. Yes. Yes. That would be the one with the one ring. Yeah.